25 trillion miles. That's how far Alpha Centauri sits from Earth. You could drive a car non-stop at highway speed for 44 million years and still not get there. But here's what makes that number truly staggering. It's our closest stellar neighbor. The next nearest sun-like star, 3 times farther. We're talking about the cosmic equivalent of your next-door neighbor, and it might as well be on another planet. Actually, it's worse than that. Much worse. Most people hear 4.37 light years and think, sure, that's far. But we've sent probes to Pluto. We've landed rovers on Mars. So Alpha Centauri is probably just a matter of time and budget, right? Not even close. The gulf between what we've accomplished in space and what it would take to reach even our nearest stellar neighbor is so vast, it borders on incomprehensible. Let me show you exactly what we're dealing with. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. I'd love to know where you're watching from and what time it is for you. Feel free to drop your location and time in the comments below. Start with something familiar. Earth to the Moon. That's 240,000 miles. We've done that trip. 12 humans have walked on lunar soil. Earth to Mars at its closest approach? About 34 million miles. We've sent multiple rovers. Voyager 1, humanity's most distant spacecraft, has traveled about 15 billion miles since its 1977 launch. Impressive, right? It's currently cruising through interstellar space, carrying its golden record of Earth sounds and images, a message in a bottle for any civilization that might find it. Here's the problem. If Voyager 1 were aimed at Alpha Centauri, which it isn't, it would take 73,000 years to arrive. Think about that timeline. The entire span of recorded human history is only about 5,000 years. Voyager would need to travel for 14 times longer than humans have been writing things down. The pyramids were built 4,500 years ago. Voyager's journey would outlast 50 pyramid-building eras. And Voyager is moving at 38,000 miles per hour. That's not slow by any reasonable standard. It's screaming through space faster than anything humans have ever built that's actually made it out of the solar system. But against the cosmic scale of interstellar distances, it's crawling. It's like trying to cross the Pacific Ocean on a paddleboard. The numbers get worse when you dig deeper. Alpha Centauri sits at 4.37 light years from Earth. A light year, the distance light travels in 1 year, equals 5.88 trillion miles. Multiply that by 4.37 and you get 25.8 trillion miles total. But let's use a different unit that might make more sense in astronomical terms. The AU, or astronomical unit, which equals the distance from Earth to the Sun, roughly 93 million miles. In those terms, Alpha Centauri is 277,600 astronomical units away. For context, Neptune, the farthest planet in our solar system, orbits at about 30 astronomical units from the Sun. Pluto at its farthest reaches about 49 astronomical units. So Alpha Centauri is nearly 5,700 times farther than Neptune. If our solar system were the size of a quarter, Alpha Centauri would be about 15 feet away, and that's our closest neighbor. You might be wondering why this distance matters so much. Why does it matter that our nearest stellar neighbor is unreachably far with current technology? Because Alpha Centauri isn't just any star system. It's actually 3 stars bound together by gravity, and recent discoveries have made it one of the most tantalizing targets in all of astronomy. The system consists of Alpha Centauri A and B, 2 sun-like stars locked in a binary dance, and Proxima Centauri, a small red dwarf that holds the title of the single closest star to our Sun at 4.24 light-years. And Proxima isn't just the closest star, it has planets. At least 2 confirmed worlds orbit that tiny red star, including Proxima b, an Earth-sized planet sitting right in the habitable zone where liquid water could theoretically exist on its surface. Think about what that means. The closest star to our Sun has an Earth-sized world in the habitable zone. This isn't some distant exoplanet thousands of light-years away that we'll never learn anything more about. This is practically in our backyard, cosmically speaking, and we can't reach it. Not with current technology, anyway. But the question of how far Alpha Centauri really is goes beyond just the raw numbers. Distance in space isn't like distance on Earth. When you're dealing with interstellar scales, you're not just fighting distance, you're fighting physics itself. Every rocket we've ever built works on the same basic principle. Throw mass out the back to push the spacecraft forward. But there's a cruel mathematical relationship called the rocket equation that governs how this works. The faster you want to go, the more fuel you need. But fuel has mass, so you need more fuel to accelerate that fuel, which means you need even more fuel to accelerate that fuel, and so on. It's exponential, not linear. Chemical rockets, the kind that got us to the moon and send satellites into orbit, can achieve speeds of maybe 150,000 miles per hour if you're really pushing it and using gravitational assists from planets. The Galileo probe, which studied Jupiter, reached about 106,000 miles per hour and holds the record for fastest speed achieved by an artificial object using chemical propulsion. At that speed, you'd need 72,000 years to reach Alpha Centauri. That's not a technology problem. That's a fundamental limitation of chemical energy. You simply cannot store enough chemical fuel on a spacecraft to accelerate it to the speeds necessary for reasonable interstellar travel. The math doesn't work. You'd need a fuel tank bigger than a planet, so scientists have proposed alternatives. Nuclear propulsion, where you're using the energy from nuclear reactions instead of chemical ones, could theoretically achieve much higher speeds. Ion drives, which accelerate charged particles using electricity rather than combustion, offer incredible fuel efficiency, though their thrust is tiny. The Deep Space One probe, launched in 1998, demonstrated ion propulsion successfully, emitting that eerie blue glow as it expelled xenon ions at tremendous velocities. But even these advanced concepts face brutal limitations. To reach Alpha Centauri in, say, 30 years, you'd need to accelerate continuously at a rate about 1,000 times faster than the Deep Space One ion engine could manage. You'd pass Pluto's orbit in just 100 days, traveling at 1,700 kilometers per second. That's fast enough to cross the United States in about 3 seconds. Getting to those speeds requires energy, enormous amounts of energy. And carrying that energy, whether as fuel or as some kind of power generation system, adds mass to your spacecraft, which requires more energy to accelerate, which requires more fuel, or a bigger power system, which adds more mass, and you're right back in the exponential trap of the rocket equation. This is where Alpha Centauri's distance becomes more than just a number. It becomes a barrier that separates the possible from the impossible, at least with anything resembling current technology. We can send robots to Mars. We can land probes on comets. We can fly spacecraft past Pluto and capture stunning images. But crossing the interstellar gulf to even our nearest neighbor, that's a different category of challenge entirely. And yet, the fact that Alpha Centauri has planets, potentially habitable planets, makes this distance feel almost tragic. Imagine if Proxima b turned out to have an atmosphere, liquid water, maybe even some form of life. We could study it with telescopes, analyze its atmospheric composition with spectroscopy, maybe even detect biosignatures, chemical signs of life. But visiting it, landing a probe there, that would require technology so far beyond what we currently possess that it might as well be magic. The system itself is fascinating beyond just the potential for habitable planets. Alpha Centauri A and B orbit each other in a complex elliptical dance that takes about 80 years to complete. At their closest approach, they're about 11 astronomical units apart, roughly the distance from our Sun to Saturn. At their farthest, they separate to about 36 astronomical units, farther than Neptune's orbit. These are both Sun-like stars. A is slightly larger and brighter than our Sun, while B is slightly smaller and dimmer, but both are similar enough that planets around them could theoretically support life. Then there's Proxima Centauri, sitting about 13,000 astronomical units away from the AB pair. That's 0.21 light-years, which sounds small until you realize it's about 430 times the radius of Neptune's orbit. Proxima is bound to the Alpha Centauri system gravitationally, but it's so far from the main pair that it takes hundreds of thousands of years to complete one orbit around them. And this tiny red dwarf, only about an eighth the mass of our Sun, is the one with the confirmed planets. Proxima b, the Earth-sized world in the habitable zone, orbits its star every 11.2 days at a distance of just 0.048 astronomical units. That's 20 times closer to its star than Earth is to the Sun. But Proxima Centauri is so much cooler and dimmer than our Sun that this close orbit places the planet right in the temperature range where water could be liquid. The planet receives about 65% of the energy Earth gets from the Sun, and its estimated surface temperature is around -39 degrees Celsius. But before you start imagining a habitable Earth-like world, there's a problem. Proxima Centauri is what astronomers call a flare star. Convection processes inside the star make it prone to sudden, dramatic changes in brightness. These flares unleash torrents of radiation, extreme ultraviolet and X-rays, that bombard any nearby planets. Proxima b receives 30 times more extreme UV radiation than Earth, and 250 times more X-rays. That kind of radiation would strip away any Earth-like atmosphere in relatively short order, geologically speaking. Models suggest the atmosphere could be torn away 10,000 times faster than happens on Earth. So while Proxima b might technically orbit in the habitable zone, actually harboring life as we know it, that's a much tougher proposition. The planet would need some kind of protective magnetic field or a continuously replenishing atmosphere to have any chance. Still, the mere existence of these planets so close to us, cosmically speaking, drives home just how frustrating Alpha Centauri's distance really is. We're not talking about some abstract point of light in a distant galaxy. We're talking about a star system close enough that, if we could just solve the propulsion problem, we could send probes there within a human lifetime. Close enough that the discovery of life there would be the most profound scientific finding in human history, but far enough that with current technology, it's completely out of reach. And that distance isn't even constant. Alpha Centauri is moving through space relative to our Sun, and it's actually getting closer. Right now, it's approaching us at about 22 kilometers per second. By the year 29,700 CE, it will have closed to just 3.26 light years, nearly a full light year closer than it is now. At that point, it will appear almost as bright in our sky as Canopus, currently the second brightest star visible from Earth. The closest approach will come around 27,000 CE, when Alpha Centauri will be just 2.9 light years away. Then it will start moving away again, gradually receding until, in about 100,000 years, it will no longer be our nearest stellar neighbor. Some other star will have claimed that title by then. But for now and for many millennia to come, Alpha Centauri is the closest star system to our own, tantalizingly near and frustratingly far. Understanding exactly how far 4.37 light years really is requires more than just knowing the numbers. You need to grasp what those numbers mean in practical terms, in terms of energy and time, and the fundamental physics that govern how fast anything can move through space. And that's where things get really interesting. So what does 4.37 light years actually mean in terms we can grasp? Let's start with something familiar and build from there. If you wanted to drive to Alpha Centauri at highway speeds, say 100 kilometers per hour, you'd need to keep driving for 44 million years. That's not a typo. 44 million years of continuous driving, never stopping for gas or sleep, or the complete evolution of multiple species. The Earth would cycle through multiple ice ages. Continents would drift across the globe. Your car would outlive entire mountain ranges. But nobody's suggesting we drive there. What about our actual spacecraft? The fastest thing we've ever built. The Helios probes, launched by NASA and Germany in the mid-1970s, hold the record for the fastest speed ever achieved by a spacecraft designed for interplanetary travel. They hit 250,000 kilometers per hour as they dove close to the Sun. Sounds impressive, right? At that speed, you could circle Earth's equator in about 6 minutes. You could reach the Moon in less than 2 hours. But to reach Alpha Centauri at that velocity, you'd need 18,000 years. The entirety of human civilization, from the first cities in Mesopotamia to your smartphone, has unfolded in less time than that journey would take. What about Voyager 1, humanity's most distant emissary, now sailing through interstellar space beyond the influence of the Sun? It's currently moving at about 17 kilometers per second. If it were pointed toward Alpha Centauri, which it isn't, it would arrive in roughly 73,000 years. The last ice age ended only 12,000 years ago. 73,000 years ago, humans hadn't even left Africa yet. These numbers start to feel abstract pretty quickly. Your brain knows 73,000 is bigger than 18,000, but both are so far beyond human experience that they lose meaning. So let's try a different approach. Think about the speed of light itself. Light travels at exactly 299,792,458 meters per second through empty space. Nothing moves faster. It's the universe's ultimate speed limit, baked into the fundamental structure of reality itself. At that speed, you could circle the Earth 7.5 times in 1 second. You could reach the moon in about a second and a quarter. The sun, 8 minutes and 20 seconds. Light from the sun is always 8 minutes old by the time it reaches Earth, which means if the sun suddenly vanished right now, we wouldn't know about it for 8 more minutes. We'd keep seeing it, keep feeling its warmth, completely unaware that it was already gone. Neptune, the most distant planet in our solar system, is about 4 light hours away. A radio signal traveling at light speed takes 4 hours to make the trip. When the New Horizons spacecraft flew past Pluto in 2015, the data it sent back took 4.5 hours to reach Earth, traveling at the speed of light the entire way. And Alpha Centauri is 4.37 light-years away. That means light itself, the fastest thing in the universe, the thing that crosses the solar system in hours, needs 4.37 years to make the journey. Not hours, not days, years. If you could somehow board a spacecraft that traveled at light speed, which is impossible for anything with mass, but bear with me, you'd still need to pack for a 4-year journey. You'd leave Earth, celebrate 4 birthdays in transit, and only then arrive at Alpha Centauri. But here's where it gets strange. From your perspective aboard that impossible light-speed ship, the trip would feel instantaneous. This is one of the bizarre consequences of Einstein's relativity. At light speed, time stops. You'd experience no duration at all. You'd leave and arrive in the same subjective moment. For everyone back on Earth, though, 4.37 years would pass. They'd wait. They'd wonder. They'd watch 4 summers and 4 winters cycle by before receiving your first signal confirming arrival. And that signal itself would take another 4.37 years to reach them, traveling back at light speed. So the round-trip communication time is 8.74 years minimum. Send a message to Alpha Centauri and wait nearly 9 years for a reply. That's assuming someone's there to reply instantly. Ask a question, wait 9 years for an answer. That's the best-case scenario, limited by the fundamental speed of causality itself. Now remember, we can't actually travel at light speed, not even close. The fastest spacecraft we've ever built, those Helios probes, reached about 0.02% of light speed. 0.02%. To reach even 1% of light speed with current technology would require energy expenditures beyond anything we can currently imagine. Einstein's equations show why. As you accelerate an object with mass, that mass effectively increases. The faster you go, the heavier you get, and the more energy you need to accelerate further. It's not a linear relationship, it's exponential. Push a spacecraft to 90% of light speed and its mass has more than doubled. Push it to 99% and its mass increases by a factor of 7. At exactly light speed, any object with mass would have infinite mass and require infinite energy. The universe itself prevents anything with mass from reaching that ultimate limit. You can get arbitrarily close, 99.9999% of light speed, if you have the energy, but you can never quite get there. So let's be more realistic. What if we could build a spacecraft that reaches 10% of light speed? That's still 50 times faster than anything we've achieved, but it's at least theoretically possible with technologies we can imagine. Things like nuclear pulse propulsion or advanced ion drives. At 10% of light speed, the trip to Alpha Centauri would take 43 years. Launch at age 25 and you'd arrive at age 68, assuming you survived the journey. It's barely within a human lifetime, and only if everything goes perfectly. But slow down and think about what 10% of light speed actually means. That's 30,000 kilometers per second. For comparison, the International Space Station orbits Earth at about 8 kilometers per second. You'd be moving nearly 4,000 times faster than the ISS. The engineering challenges are staggering. At those speeds, even a grain of dust becomes a devastating projectile. Space isn't perfectly empty. There are atoms floating around, tiny particles of ice and rock, cosmic dust. Hit a speck of debris at 30,000 kilometers per second, and the impact energy would be colossal. Your spacecraft would need shielding that could withstand continuous bombardment by what are essentially microscopic bombs. Then there's the fuel problem. Chemical rockets are completely out of the question. The amount of conventional rocket fuel needed to accelerate even a small spacecraft to a significant fraction of light speed would exceed the mass of the spacecraft itself by factors of millions or billions. It's physically impossible with chemical propulsion. That's why scientists think about alternatives. Ion drives that chute charged particles out the back, providing tiny but continuous thrust over years or decades. Nuclear rockets that achieve much higher exhaust velocities than chemical reactions can produce. Antimatter engines that could theoretically approach the efficiency limits of physics itself, though we currently have no way to produce or store antimatter in useful quantities. Or more exotic concepts: solar sails pushed by sunlight, laser-driven light sails accelerated by massive ground-based laser arrays, interstellar ramjets that scoop up hydrogen from the space between stars and use it as fuel. Each concept has serious technical hurdles, but at least they're not ruled out by fundamental physics. The point is, even with technologies far beyond anything we have today, reaching Alpha Centauri is hard. Not impossible, but hard in ways that make the Apollo program look like a weekend camping trip. And that's just getting there. What about actually doing something useful once you arrive? A flyby mission is one thing. Scream past at 10% of light speed, snap some photos and keep going into deep space forever. But if you want to slow down, to enter orbit around one of the stars, to study the system in detail, you need to shed all that velocity you worked so hard to gain, which means you need even more fuel, even more mass, even more energy. A mission that could actually stop at Alpha Centauri and return to Earth would be vastly harder than a one-way trip. You'd need to accelerate, then decelerate, then accelerate again for the return journey, then decelerate one final time when you reached Earth. Each phase requires enormous amounts of energy. With current technology, a round-trip mission to Alpha Centauri is flatly impossible. With foreseeable near-future technology, things we can at least imagine building in the next century or two, it would still take multiple human lifetimes and resources on a scale that dwarfs anything humanity has ever attempted. This is why Alpha Centauri occupies such a frustrating place in our cosmic neighborhood. It's right there. Compared to the vast distances between galaxies, or even just to other stars we can see with the naked eye, Alpha Centauri is practically in our backyard. The next nearest sun-like star is 3 times farther away, and yet it's completely beyond our reach. We can see it. We can study it with telescopes. We can detect planets orbiting its stars. We can measure its motion through space with exquisite precision. But we can't go there. Not yet. Maybe not for centuries. That gap between what we can observe and what we can touch, defines modern astronomy. We live in an era where we can detect the atmospheres of planets hundreds of light years away, but can't send a probe to the star system next door. The physics of distance hasn't changed. Light still takes 4.37 years to cross the gulf between here and there, but our ability to observe across that gulf has exploded. We've gone from barely knowing Alpha Centauri was 3 stars instead of 1 to detecting Earth-sized planets in its habitable zones, which makes the distance feel even more frustrating, because now we know what's there. We know there are worlds orbiting those distant suns. We know at least some of them occupy the temperature range where liquid water could exist. We know the basic parameters: mass, orbital period, stellar radiation. But we can't know the crucial details. We can't see the surface. We can't analyze the atmosphere directly. We can't search for biosignatures with the kind of precision that would let us definitively answer whether life exists there, all because of 4.37 light years of empty space. That distance shapes everything about how we think about interstellar exploration. It's the minimum distance we'd need to cross to visit another star, the benchmark against which all other stellar distances are measured, the closest we can possibly get to answering the question of whether we're alone in the universe without looking in our own solar system. Understanding this distance, really understanding it, not just knowing the number but feeling what it means, is essential to grasping humanity's place in the cosmos. We're residents of a single star system, separated from our nearest stellar neighbors by gaps that make the distances within our own solar system look like nothing. The distance doesn't just separate us physically. It separates us temporally in ways that fundamentally change what exploration even means. Every signal we send to Alpha Centauri takes 4.37 years to arrive. Every response takes another 4.37 years to come back. That's a minimum round-trip communication time of 8.74 years. You could ask a question as a college freshman and get your answer after you've graduated, started a career, maybe had kids. This time lag isn't a technical limitation we can engineer around. It's physics. The speed of light is the universe's speed limit, and there's no shortcut. What does that mean for exploring Alpha Centauri? It means any mission we send will be fundamentally different from every space mission humans have ever attempted. When we sent robots to Mars, mission controllers could make decisions and implement them within minutes. When something went wrong with the Mars rovers, engineers could troubleshoot, send new commands, and see the results the same day. Even with the Voyager probes now beyond the heliopause at the edge of our solar system, we can still communicate with them. The signal takes hours, but it's still real-time enough to matter. A probe at Alpha Centauri. That's autonomous in a way nothing we've built has ever needed to be. If something goes wrong, you can't fix it from Earth. The probe won't even know you've sent help for over 4 years. By the time your solution arrives, the mission could have been over for years. This creates bizarre scenarios that mission planners have never had to consider. Imagine detecting an interesting planet around Proxima Centauri and wanting to take a closer look. On Earth, you'd make that decision, send the command, and wait. 4.37 years later, your command arrives. The probe alters course, takes new images, and transmits them back. 4.37 more years pass. You receive the data 8.74 years after you made the decision to look. In that time, the probe has continued following whatever autonomous protocols it had, potentially missing other opportunities. or making choices you would have overridden if you could have communicated in real time. Or consider this. A probe reaches Alpha Centauri after decades of travel. It begins transmitting data back to Earth. 4.37 years later, we receive the first images. But by the time those images arrive, the probe has already completed its primary mission and moved on to whatever secondary objectives were programmed into it. We're not observing the mission as it happens. We're watching a recording of something that finished years ago. The temporal disconnect cuts both ways. Any decisions made on Earth based on data from Alpha Centauri are decisions about a system as it was over 4 years ago. If Proxima Centauri undergoes one of its characteristic stellar flares, we won't know about it until the light reaches us 4.24 years later. If a probe we sent there gets damaged by that flare, we won't know that for another 4.24 years. By the time we learn about the problem, it happened over 8 years ago. The probe has either fixed itself or it hasn't. Our knowledge is always nearly a decade behind reality. This time lag would shape everything about an Alpha Centauri mission. The probe would need to be programmed with decision-making capabilities that far exceed anything we've given spacecraft before. It would need to handle scenarios we can't predict, make trade-offs we haven't explicitly programmed, and essentially act as an independent agent, carrying out human intentions without human guidance. Some engineers have proposed sending multiple probes in sequence, each one benefiting from what previous missions discovered. But even that strategy runs into the time problem. You send probe 1. 20 to 30 years later, it arrives and begins transmitting data. 4 years after that, you receive it. You spend a few years analyzing the results and designing probe 2 based on what you learned. You launch it. Another 20 to 30 years pass. Now you're looking at a mission timeline measured not in decades, but in generations. The people who launched probe 1 are likely retired or dead by the time probe 2 arrives. The scientists who designed probe 2 based on probe 1's data might not live to see their creation reach its destination. This multi-generational aspect of Alpha Centauri exploration raises questions that go beyond engineering. How do you maintain institutional knowledge across periods longer than most careers? How do you keep funding and political support alive for projects that won't show results until long after current decision makers are gone? How do you build spacecraft using technologies that won't be obsolete by the time they arrive? That last question is particularly thorny. Technology improves exponentially. A probe we build today using cutting-edge technology and launch toward Alpha Centauri would be based on 30-year-old technology by the time it arrived. During the decades of its journey, we'd likely develop better propulsion systems, better sensors, better computers. There's a real possibility that a probe launch 20 years from now, using technologies we haven't invented yet, could overtake our current probe and arrive first. This creates what some call the weight calculation. Is it better to launch now with current technology, or wait for better technology and launch later? The math on this is frustrating. If technology improves fast enough, waiting is always the better choice. But if everyone waits for better technology, no one ever launches. And if someone does launch, and technology then improves dramatically, they've wasted resources on an obsolete mission. There's no clean answer, just trade-offs between the certainty of current capabilities and the promise of future improvements. The distance also affects how we'd interpret any data we receive. Say we detect something unusual around one of Alpha Centauri's planets. something that might indicate biological activity. By the time we receive that signal, we're seeing that planet as it was over 4 years ago. If we want to confirm the finding with additional observations, we need to send new commands, wait 4 years for them to arrive, wait for the observations to be made, then wait another 4 years for the results. That's nearly a decade to confirm a single observation. Scientific research as we know it, with its cycles of hypothesis, observation, and refinement, would operate on timescales that span decades rather than months or years. This creates an interesting epistemological problem. Our knowledge of Alpha Centauri would always be fundamentally historical. We could never know the current state of the system, only its past. The present would forever remain inaccessible, hidden behind the light travel time barrier. Even if we somehow sent humans there, something that seems impossible, but let's imagine it, they would be experiencing a present that Earth wouldn't learn about for over 4 years. They'd be making discoveries, seeing sights, learning things that Earth wouldn't know existed for half a decade. The two locations would be causally disconnected, unable to share a common now. Einstein's relativity tells us there's no universal present anyway. What counts as now depends on your reference frame, but in practical terms, for places close enough to communicate quickly, we ignore this. It doesn't matter. For Alpha Centauri, it matters profoundly. Earth and Alpha Centauri can't share experiences in real time, can't coordinate actions beyond the most basic pre-planned sequences, can't have conversations. The distance forces a kind of isolation that's absolute within the constraints of known physics. Some physicists have speculated about shortcuts, wormholes that could connect distant points in space without requiring travel through the space between them. Warp drives that could somehow compress space in front of a ship and expand it behind, allowing faster than light travel without actually moving faster than light locally. These ideas emerge from legitimate physics. General relativity does allow for exotic space-time geometries that could, in principle, permit such things. But the gap between mathematical possibility and engineering reality is vast. Wormholes, if they can exist at all, would require exotic matter with negative energy density. Warp drives would need to manipulate space-time itself using energy sources we can barely imagine. These aren't technologies waiting to be built. They're speculative ideas that might be physically impossible. So we're left with the straightforward conclusion. Alpha Centauri is 4.37 light-years away. That distance is absolute. It can't be shortened. It creates a time lag that can't be eliminated. And it means that any exploration of our nearest stellar neighbor will be fundamentally different from any exploration humans have ever attempted. Which brings us back to what we actually know about the system. Not from probes we've sent there, we haven't sent any, but from observations made across that vast distance. What have we learned about Alpha Centauri by studying the light that makes that 4-year journey to our telescopes? The answer turns out to be quite a lot. And some of it changes the entire calculus of why we'd want to go there in the first place. The first systematic observations of Alpha Centauri began with spectroscopy. By splitting the light from the system into its component wavelengths, astronomers could read the chemical signatures embedded in that light, like a cosmic barcode. Every element absorbs and emits light at specific wavelengths. Hydrogen has its pattern, helium has another, iron, carbon, oxygen. Each leaves its fingerprint. What they found was remarkably similar to our Sun. Alpha Centauri A, the larger of the two main stars, is a G-type star just like our Sun, though slightly more massive and luminous. Its spectrum reveals iron, silicon, magnesium, all the elements we'd expect in a solar-type star. The abundances are close to solar values, suggesting both stars formed from similar material, possibly even from the same molecular cloud that birthed our Sun billions of years ago. Alpha Centauri b is a K-type star, smaller and cooler than A, but still within the broad category of stars that could potentially host habitable planets. Together, these two stars orbit their common center of mass every 79 years in an elliptical dance that brings them as close as 11 astronomical units, roughly Saturn's distance from the Sun, and separates them to 35 astronomical units beyond Neptune's orbit. But it's the third member of the system that changed everything about why we care about Alpha Centauri. Proxima Centauri was discovered in 1915 by Robert Innes, a Scottish astronomer working in South Africa. He noticed a faint red star that seemed to be moving through space at the same velocity as the bright Alpha Centauri AB pair. The proper motion matched, the parallax matched. It was part of the system. For decades, Proxima was just a curiosity. A dim red dwarf, barely visible even in telescopes, contributing almost nothing to the system's overall light. If you were standing on a planet orbiting Alpha Centauri A, Proxima would look like a faint red point in your sky, unremarkable and easily overlooked. Then in 2016, everything changed. A team of astronomers announced they'd found a planet orbiting Proxima Centauri. Not just any planet, a planet in the habitable zone, the region where temperatures might allow liquid water to exist on the surface. They called it Proxima b, and it became instantly famous as the closest potentially habitable exoplanet to Earth. The discovery method was radial velocity. By measuring tiny wobbles in Proxima Centauri's motion caused by the gravitational tug of an orbiting planet, astronomers could infer the planet's presence. The wobble had a period of 11.2 days. That's how long Proxima b takes to complete one orbit, 11 days. For comparison, Mercury takes 88 days to orbit our Sun. Proxima b is extraordinarily close to its star, just 7 million kilometers away, roughly 5% of the distance between Earth and the Sun. But here's why it's in the habitable zone. Proxima Centauri is a red dwarf, much cooler than our Sun. Its habitable zone exists much closer in. What would be a scorched Mercury-like orbit around a Sun-like star becomes potentially temperate around a red dwarf. Proxima b receives about 65% of the radiation Earth gets from the Sun. Not too hot, not too cold, at least in terms of raw energy. The problem is what kind of radiation it receives. Red dwarfs are violent stars, especially when young. They produce massive flares, sudden eruptions of energy that blast their surroundings with X-rays and ultraviolet radiation. Proxima Centauri is no exception. It's a flare star, prone to outbursts that can increase its brightness by orders of magnitude in minutes. Proxima b, orbiting so close, gets hit with this radiation at point-blank range. Studies suggest the planet receives 30 times more extreme ultraviolet radiation than Earth, and 250 times more X-rays. Over billions of years, this radiation would strip away any atmosphere the planet might have had unless something protected it. A strong magnetic field could help. Earth's magnetic field deflects much of the solar wind and radiation that would otherwise erode our atmosphere. If Proxima b has a similar protective shield, it might retain an atmosphere, but we don't know if it does. We can't measure magnetic fields on exoplanets yet. There's another problem. Proxima b is likely tidally locked. One side permanently faces the star, baked by constant radiation. The other side faces eternal night, potentially frozen solid. This isn't necessarily fatal to habitability. Atmospheric circulation could distribute heat around the planet, but it creates conditions utterly unlike Earth. Still, the mere possibility of a planet in the habitable zone, just 4 light-years away, electrified the scientific community and the public. Finally, a target, a destination, a place we could imagine sending probes to explore. Then came more discoveries. In 2020, astronomers announced a second planet in the Proxima Centauri system. Proxima d, even smaller than Proxima b, orbits much closer to the star with a period of just 5 days. It's likely too hot for liquid water, more of a super-Mercury than a potential Earth. And there might be a third planet, Proxima c, a possible super-Earth orbiting every 5 years at a distance where water would be frozen. The evidence is less certain, still being debated, but if it exists, the Proxima system would have at least 3 worlds, a miniature planetary system around our nearest stellar neighbor. But the surprises didn't stop with Proxima. In late 2024, observations from the James Webb Space Telescope revealed something unexpected around Alpha Centauri A. A bright blob in the infrared, positioned close to the star, visible in August observations, but gone by February. The team analyzing the data suggested it might be a Saturn-mass planet, a gas giant orbiting roughly twice Earth's distance from the Sun. The problem is the blob disappeared. Follow-up observations in February and April 2025 found nothing. This doesn't necessarily mean it wasn't real. Planets move, and depending on their orbital position, they can pass behind their star or move into positions where they're impossible to detect. But it creates uncertainty. If the planet exists, it would be one of the closest gas giants to Earth ever discovered, orbiting a sun-like star in a system we could potentially reach. But "if" is doing heavy work in that sentence. The detection needs confirmation, more observations, more data points. This is the frustration of studying Alpha Centauri. We're close enough to care deeply about what's there, but still too far to get clear answers quickly. Every observation requires careful planning. Every follow-up takes months or years, and even our best instruments are pushing their limits to detect these worlds. The distances involved create another layer of complexity. Proxima Centauri is 13,000 astronomical units away from Alpha Centauri A and B. That's about 1/5 of a light year. In one sense, Proxima is part of the Alpha Centauri system. It's gravitationally bound, orbiting the same galactic center at the same velocity. But in another sense, it's profoundly separate. If you were standing on a planet around Alpha Centauri A, Proxima would be a faint point of light in your sky, dimmer than many stars visible from Earth. The travel time between the two parts of the system, even at high speeds, would be measured in centuries with current technology. They're neighbors in cosmic terms, but isolated in practical ones. This raises questions about planetary formation. Did planets form around all 3 stars independently? Or could gravitational interactions between the 3 stars have disrupted planet formation in some regions while allowing it in others? The orbits of Alpha Centauri A and B bring them close enough together that their gravitational influence extends well beyond where planets could stably orbit. Any planet forming too far from either star would eventually be perturbed, ejected, or captured by the other star. Computer simulations suggest planets could exist in stable orbits, close to either A or B individually, or in wide orbits around both stars as a binary. But the middle zones would be chaotic, unstable over millions of years. This constrains where we should look for planets and what kinds of planetary systems we might find. The age of the system matters too. Alpha Centauri is old, probably around 6 billion years, older than our Sun by 1.5 billion years. If planets formed early in the system's history, they've had time to evolve, to develop atmospheres, to undergo geological processes we can only guess at. An Earth-like planet in the system would have had more time for life to emerge and evolve than Earth itself has had. But age cuts both ways. Proxima Centauri, despite being part of the same system, might not have formed at the same time. Some models suggest it could have been captured later, a wandering red dwarf that happened to pass close enough to Alpha Centauri AB to become gravitationally bound. If that's true, its planets might be younger or older, or might have formed under completely different conditions. We're piecing together the story from fragmentary evidence. Spectroscopic measurements tell us about composition. Radial velocity measurements reveal planets through their gravitational effects. Direct imaging, what Webb attempted with Alpha Centauri A, can potentially show us planets themselves, but only under ideal conditions and with enormous technical challenges. Every piece of data arrives after a 4-year journey. Every observation represents the system as it was 4 years ago, and every discovery raises more questions than it answers, creating a portrait of our nearest stellar neighbor that's simultaneously detailed and frustratingly incomplete. Yet this incomplete picture is enough to transform Alpha Centauri from an abstract point of light into something more, a place with planets, possibly with worlds where water flows, potentially with environments where life could exist. The closest such place to Earth we've yet found. That single fact, that there are planets around our nearest stellar neighbor, changes the entire calculation of whether trying to reach it makes sense, which means the decision to attempt reaching it isn't purely scientific curiosity anymore. It's not just because it's there. There's a destination worth reaching, a place that might answer questions we've been asking since we first looked up and wondered if we were alone. The technology required to make that journey would need to overcome obstacles that currently exist only in theoretical physics textbooks. Start with the most fundamental problem: energy. To accelerate even a small probe to a meaningful fraction of light speed requires energy on scales that dwarf anything human civilization has ever harnessed. Consider the numbers. A spacecraft the size of a cell phone, weighing perhaps a gram, would need to reach 20% of light speed to make the trip to Alpha Centauri in a human lifetime. The kinetic energy of that gram at that velocity equals the energy released by detonating several kilotons of TNT. Scale, that up to anything resembling a traditional spacecraft. And you're talking about energy requirements that exceed the total annual energy consumption of entire nations. This is where breakthrough Starshot entered the conversation. Announced in 2016 by Yuri Milner and Stephen Hawking, with backing from Mark Zuckerberg, the project proposed something audacious. Instead of carrying fuel, which adds weight, which requires more fuel, creating a vicious cycle that makes high speeds impossible. They suggested using light itself as propulsion. The concept sounds almost magical. Build a spacecraft smaller than your hand. Attach an ultra-thin reflective sail. Launch it into space, then blast it with powerful lasers from Earth. The photons from those lasers would transfer momentum to the sail, accelerating the craft without consuming any onboard fuel. Within 10 minutes of laser acceleration, the probe would reach 20% of light speed. At that velocity, it would pass Mars in hours. It would reach Alpha Centauri in about 20 years. 20 years. A child born when the mission launched would still be young enough to see the results. Data from another star system arriving within a human lifetime. Images of alien worlds captured from just beyond their atmospheres. But the gulf between concept and reality proved wider than the gulf between stars. The technical challenges stacked up like a wall that grew taller the closer you examined it. Start with the lasers themselves. To accelerate a gram-scale spacecraft to 20% of light speed in 10 minutes requires a laser array capable of outputting 100 gigawatts. For context, the largest power plants on Earth generate around 1 gigawatt. You'd need the equivalent of 100 massive power plants, all feeding energy into a laser system that doesn't actually exist yet. All focused with perfect precision on a sail the size of a postcard, receding at thousands of kilometers per second. The sail presents its own nightmare of engineering constraints. It needs to be reflective enough to bounce photons efficiently, light enough to accelerate quickly, strong enough to survive the laser bombardment without vaporizing, large enough to catch sufficient photons, small enough to not be unmanageable. And it needs to maintain its shape to micron-level precision, while being blasted with more energy than any material in history has been asked to withstand. Then there's the problem of aiming. The spacecraft would accelerate from 0 to 60,000 kilometers per second in 10 minutes. Keeping a laser beam focused on something that small, moving that fast, from a planet that's rotating, requires pointing precision that makes threading a needle while blindfolded seem trivial by comparison. The slightest deviation and you're not pushing the sail anymore. You're just heating random patches of space. Assume you solve all that. The probe reaches cruising speed and begins its 20-year journey. Now it faces a different hazard, the interstellar medium. Space between stars isn't empty. It's filled with hydrogen atoms, dust particles, cosmic rays. At 20% of light speed, colliding with even a single grain of dust releases energy equivalent to a small explosion. The probe would be sandblasted by atoms, each impact carrying enough energy to damage sensitive electronics. You can't armor against this. Armor adds weight, and weight destroys the entire concept. You can't dodge the particles because you have no propulsion system capable of maneuvering at those speeds. You just have to hope the path is clear enough that the probe survives. 20 years pass. The probe reaches Alpha Centauri, screaming past Proxima Centauri at 20% of light speed. It has no brakes, no way to slow down. It gets one shot at gathering data during a flyby that lasts hours at most. Every instrument, every camera, every sensor has to work perfectly after 2 decades of exposure to cosmic radiation and high-speed particle impacts. But the real problem emerges when you try to send that data home. The probe is 4 light-years away, traveling away from Earth at 60,000 kilometers per second. To transmit data, it needs power, a lot of power. Radio signals obey the inverse square law. they weaken with the square of the distance. At 4 light years, even a powerful transmitter becomes a whisper. The probe weighs a gram. Where does transmission power come from? Solar panels are useless at Alpha Centauri if the probe is moving away from the stars. Batteries capable of storing enough energy for transmission would weigh far more than the entire probe. The proposal suggested using the sail itself as an antenna, but that requires engineering precision that borders on fantasy. And even if you solve the power problem, you face the bandwidth problem. Transmitting a single high-resolution image from that distance could take months. Video would take years. The data returned from a mission that cost billions and represented humanity's first venture to another star might be a handful of pixelated images arriving after years of transmission. Breakthrough Starshot acknowledged these challenges. The project was structured as a long-term research program, not an immediate mission. The goal was to investigate whether the concept was even feasible, to identify the technical barriers, to begin developing solutions. What actually happened was more sobering. The promised $100 million in funding largely failed to materialize. Research grants totaled in the hundreds of thousands rather than millions. The work that did happen revealed problem after problem with no clear solution. By 2024, the project had effectively gone dormant, with no official cancellation but no visible progress either. This doesn't mean the concept was wrong. It means the gap between what we can do and what we need to do is wider than anticipated, perhaps much wider. Other approaches exist, at least on paper. Nuclear pulse propulsion, where you detonate small nuclear explosions behind a spacecraft to push it forward. Fusion ramjets that scoop up hydrogen from space and fuse it for propulsion. Antimatter engines that annihilate matter and antimatter for maximum energy release. Generation ships that take centuries to make the journey, with multiple human generations living and dying en route. Each approach faces obstacles that make Starshot's challenges look manageable. Nuclear pulse propulsion violates international treaties and creates radiation hazards. Fusion ramjets require technology we haven't developed and may not work in practice because the interstellar medium isn't dense enough. Antimatter doesn't exist in meaningful quantities and would require more energy to produce than it would release. Generation ships require life support systems that function perfectly for centuries and social structures that remain stable across dozens of generations. You begin to see why no serious proposal for crewed interstellar flight exists. The problems aren't just technical, they're fundamental. They emerge from physics itself, from the relationship between mass, energy, and velocity, from the speed of light limit that makes the universe enormous and our speeds comparatively glacial. Which returns us to the central question. If Alpha Centauri is effectively unreachable with any technology we can currently envision, does it matter that planets orbit there? Does the knowledge that worlds exist 4 light-years away change anything if those worlds might as well be 4 million light-years away, for all the difference it makes to our ability to reach them? In one sense, no. The planets remain remote, inaccessible, beyond the practical reach of human exploration for the foreseeable future. We can observe them from Earth. We can study their light spectra, measure their masses, estimate their compositions. But visiting them, landing on them, walking their surfaces, that remains science fiction. Yet in another sense, their mere existence shifts the calculation. Because now we know. Not that we suspect or theorize or hope, but that we know for certain. Other worlds orbit other stars. And those worlds aren't scattered randomly through the galaxy at distances that reduce them to pure abstraction. The nearest ones are right there, close enough that light from their suns reaches us in the time it takes to complete an undergraduate degree. This knowledge creates pressure, technological pressure to develop better propulsion, economic pressure to invest in capabilities that might eventually enable such missions, cultural pressure to think beyond our solar system as the boundary of human civilization. The planets around Alpha Centauri are destinations now, not just points of light. And destinations create imperatives that mere possibilities never could. Human history suggests that when destinations become known, eventually someone figures out how to reach them. The Pacific Islands seemed impossibly remote until Polynesian navigators crossed thousands of miles of open ocean in outrigger canoes. Antarctica was unreachable until it wasn't. The moon existed for millions of years before 1969, but once we knew it was a place, reaching it became inevitable. Alpha Centauri's planets might follow that pattern. Not soon, probably not within our lifetimes or our children's lifetimes, but the knowledge that they exist makes them targets for future capabilities we can't yet imagine. Technology that would seem like magic to us, the way our technology would seem like magic to someone from the 1800s. The question isn't whether we should try to reach Alpha Centauri. The question is what we learn in the attempt. Because the technologies we develop trying to reach Alpha Centauri will transform everything else we do in space. Consider what happened during the Apollo program. NASA didn't just build rockets to reach the moon. They created integrated circuits, developed fuel cells, invented new materials, pioneered computer miniaturization, technologies that had nothing to do with lunar exploration, except that solving lunar problems required inventing them. And once invented, they spread everywhere. The same pattern would repeat for Alpha Centauri, but amplified. Any propulsion system capable of reaching another star system would revolutionize travel within our own solar system first. A spacecraft that could reach 20% light speed would get to Mars in minutes instead of months, to Jupiter in hours instead of years. The entire solar system would shrink to the scale of a long road trip. But propulsion represents just one category. Communications technology capable of sending data across 4 light years would handle every distance within the solar system trivially. Power systems that could operate continuously for decades without refueling would enable missions that current spacecraft can't attempt. Life support that could sustain humans for generations would make permanent space habitation straightforward. The knowledge gained would extend beyond hardware. Understanding how to navigate interstellar space requires mapping gravitational fields with precision we haven't achieved. Protecting against radiation in deep space demands materials and shielding we haven't developed. Maintaining systems across decades or centuries requires reliability standards we haven't met. Each of these challenges exists whether we're aiming for Alpha Centauri or just trying to build better satellites. But the Alpha Centauri goal creates urgency. It provides a concrete target that justifies investment in capabilities that would otherwise remain theoretical. This explains why NASA and other space agencies study interstellar mission concepts, even knowing they won't launch such missions soon. The studies themselves advance the field. They identify which problems need solving. They suggest which technologies deserve development. They create roadmaps that guide research in productive directions. Breakthrough Starshot demonstrated this principle despite its current uncertain status. The project brought together physicists, engineers, materials scientists to think seriously about lightsail propulsion. Even if Starshot never launches, the work produced insights about laser arrays, ultra-lightweight materials, precision manufacturing at nanometer scales. Insights that apply to other projects, other goals, other missions. You're probably wondering whether any of this matters if we can't actually reach Alpha Centauri in any reasonable time frame. Here's why it does. The value isn't reaching Alpha Centauri specifically. The value is building capabilities that make reaching Alpha Centauri theoretically possible, because those capabilities transform what we can accomplish everywhere else. Think about the International Space Station. Nobody built the ISS because we desperately needed a laboratory in low Earth orbit. We built it because maintaining a permanent human presence in space requires solving thousands of small problems. How do you recycle water in zero gravity? How do you grow food without soil? How do you maintain equipment when you can't just order replacement parts? Solving those problems for the ISS created knowledge that applies to every future space habitat, whether on the Moon, Mars, or eventually in deep space. The ISS wasn't the destination, it was the training ground. Alpha Centauri serves the same function for interstellar capability. We don't need to actually send humans there to benefit from trying to figure out how we would send humans there. Which brings us to an uncomfortable question. If the real value lies in developing the technology rather than reaching the destination, why not just develop the technology without the expensive, probably impossible mission goal? Because humans don't work that way. We need concrete goals. Abstract capability development doesn't inspire the public, doesn't justify budgets, doesn't motivate researchers to solve hard problems. The moon landings didn't happen because NASA wanted to advance rocketry. They happened because President Kennedy set a specific goal with a deadline. Reach the moon before 1970. That specificity created focus that general technological advancement never could. Alpha Centauri provides the same focus for interstellar capability. It's specific, measurable, achievable in principle, if not in practice with current technology. It gives researchers something concrete to aim for, rather than vague aspirations about advancing propulsion or improving efficiency. The planets orbiting Alpha Centauri strengthen this dynamic. Now we're not just trying to reach another star system. We're trying to reach worlds that might harbor conditions for life. That might teach us something about how planets form. That might show us examples of geology, weather, chemistry operating under different conditions than Earth's. Scientific motivation combines with exploration motivation. Both reinforce the engineering motivation, and together they create pressure to develop capabilities that transform space exploration generally. But there's another dimension to consider, one that extends beyond technology or science into questions about humanity's long-term future. Our solar system won't remain habitable forever. The sun will eventually expand into a red giant, engulfing Earth and the inner planets. That won't happen for billions of years, but it will happen. At some point, if humanity still exists, we'll need to leave. More immediately, various existential risks threaten our survival as a species. Asteroid impacts, supervolcano eruptions, nuclear war, pandemics, climate change. Some of these we might prevent or mitigate. Others we can't control. Establishing human presence beyond Earth provides insurance against planetary-scale catastrophes, but staying within our solar system only partially addresses this problem. A catastrophe that destroys Earth might also threaten Mars or the Moon or orbital habitats. They all orbit the same star, exist within the same gravitational well, share many of the same vulnerabilities. True long-term survival requires spreading to other star systems. Not because we'll need that capability soon, but because eventually, on timescales of thousands or millions of years, our descendants might need options we don't currently have. Alpha Centauri represents the first step in that multi-generational project. Not because we'll colonize it next century, but because learning how to reach it teaches us how to reach other stars. And reaching other stars eventually becomes necessary if humanity intends to survive indefinitely. This perspective transforms the question. We're not asking whether we can reach Alpha Centauri with current technology. Obviously, we can't. We're asking whether we should begin developing capabilities that might eventually enable such missions. Knowing the development itself creates value regardless of whether the mission launches. The answer seems clearly yes, because the alternative is accepting permanent confinement to one solar system, one planet, one basket for all of humanity's eggs. But accepting this answer creates new questions. How much should we invest in such long-term capabilities? What priority should they receive compared to more immediate challenges? How do we balance resources between solving problems on Earth and developing capabilities for leaving Earth? These questions don't have simple answers. Different people reasonably disagree about proper priorities, about how much attention humanity should devote to space exploration versus other goals. What's clear is that the discovery of planets around Alpha Centauri changed the calculation. Before we knew those planets existed, interstellar travel remained pure abstraction. Interesting theoretically, but disconnected from anything real. Now we know specific worlds orbit specific stars at specific distances. We can point telescopes at them, measure their properties, estimate their characteristics. They're not hypothetical anymore. They're actual places that exist whether we reach them or not. And knowing they exist creates pull. Psychological pull toward developing capabilities to study them more closely. Economic pull toward technologies that might enable such missions. Cultural pull toward thinking of humanity as a multi-system species rather than a planetary one. That pull won't translate into missions tomorrow or next decade. The obstacles remain formidable. The costs remain astronomical. The timescales remain discouraging. But pull accumulates over time. It influences research priorities, funding decisions, career choices. It shapes which problems seem worth solving, which technologies seem worth developing, which goals seem worth pursuing. The students studying aerospace engineering today grew up knowing exoplanets exist around other stars. That knowledge shapes their ambitions differently than previous generations, who could only speculate. Some of them will spend careers developing technologies that bring interstellar flight incrementally closer to feasible, and their students will build on that work. And their students will build further, until eventually someone looks up and realizes the impossible has become difficult. And the difficult has become expensive, and the expensive has become merely challenging. That's how impossible things become possible. Not through sudden breakthroughs, but through accumulated incremental progress across generations. each generation pushing the boundary slightly further, each advance making the next advance slightly easier. Alpha Centauri's planets provide the target that focuses this multi-generational effort. They transform interstellar flight from abstract concept to concrete engineering challenge. They create specific questions that demand specific answers. They turn "someday we might" into "eventually we will." Which means the real question isn't whether we can reach Alpha Centauri. It's whether we're willing to start the journey knowing we won't see the destination. Human history suggests we are. We plant trees we won't sit under. We build cathedrals we won't see completed. We invest in research that won't pay off for decades. We think beyond our own lifetimes when the goal seems worthy enough. Reaching other star systems seems worthy enough. Not because we need to next year or next century, but because the journey itself transforms us. Because the capabilities we develop enable achievements we can't yet imagine. Because the simple act of trying expands what humanity considers possible. The planets around Alpha Centauri wait patiently in the dark. They don't care whether we reach them. They'll continue orbiting their stars long after our civilization has ended. But knowing they exist changes us. It shifts our perspective from earthbound to starbound. It makes the galaxy feel less empty and more like territory waiting for exploration. That shift in perspective might be the most valuable thing Alpha Centauri gives us. Not a destination we can reach, but a horizon we can aim for. Aiming toward Alpha Centauri changes us even before we get there. Consider what happens when humanity collectively points towards something impossibly distant. The goal itself becomes less important than what we build while pursuing it. The Apollo program never aimed primarily at the moon. It aimed at demonstrating technological supremacy during the Cold War. But the technologies developed along the way, integrated circuits, computer miniaturization, advanced materials, transformed industries that had nothing to do with space. GPS satellites, weather forecasting, global communications. All downstream effects of chasing one distant goal. Interstellar flight follows similar logic. We won't develop the capability to reach Alpha Centauri by focusing exclusively on Alpha Centauri. We'll develop it by solving thousands of smaller problems that collectively make interstellar flight possible. Advanced propulsion systems that enable faster solar system exploration. Better radiation shielding that protects astronauts on Mars missions. Life support systems capable of operating for decades without resupply. Each advancement serves immediate practical purposes while incrementally closing the gap toward interstellar capability. This creates economic justification that pure exploration cannot provide. Congress won't fund a 70,000-year mission to Alpha Centauri, but it will fund technologies that reduce Mars mission costs, extend satellite lifespans, enable asteroid mining. Those same technologies push interstellar flight from impossible toward merely improbable. The psychological shift matters more than the technology. Previous generations grew up knowing stars were distant, unreachable points of light. Current generations know specific planets orbit those stars. Future generations will grow up seeing detailed images of exoplanet atmospheres, spectroscopic analyses of their compositions, maybe even surface features. That familiarity transforms abstract destinations into concrete places worth reaching. Think about how moon missions changed public consciousness. Before Apollo, the moon represented romantic abstraction. After Apollo, it became somewhere humans had walked. The transition from abstract to actual fundamentally altered how we think about space. Exoplanet discoveries around Alpha Centauri create similar transitions. Those worlds exist whether we acknowledge them or not. But knowing they exist changes how we think about our place in the cosmos. Proxima b orbits 4.24 light-years away. That distance hasn't changed, but our relationship to that distance has. Before we knew Proxima b existed, 4.24 light-years represented empty space between stars. Now, it represents the distance to a specific world with specific characteristics orbiting a specific star. The number stays constant, but its meaning transforms. This transformation drives technological development in unexpected directions. Material scientists working on better solar panels for Earth applications discover techniques applicable to light sails. Computer engineers developing AI for autonomous vehicles create algorithms useful for spacecraft navigation across interstellar distances. Biologists studying extremophiles in Earth's deep ocean inform models of potential life around Proxima Centauri. Progress in one domain feeds progress in another, until the accumulated knowledge base makes previously impossible things merely difficult. The timeline matters less than the trajectory. Whether we reach Alpha Centauri in 300 years or 3,000 becomes less relevant when viewed across civilization timescales. What matters is establishing trajectory, demonstrating that humanity is collectively moving toward interstellar capability rather than away from it. Each generation doesn't need to complete the journey. It just needs to advance further than the previous generation managed. Ancient civilizations understood this. They built cathedrals knowing completion would take centuries. They planted orchards knowing the fruit would feed their grandchildren. They invested in irrigation systems that would serve communities for generations. Modern civilization often forgets this long-term thinking, focusing on quarterly earnings and election cycles. Interstellar flight forces us to recover that perspective. You can't optimize quarterly returns when planning missions that span lifetimes. You can't campaign on promises that won't materialize for centuries. The very act of seriously pursuing Alpha Centauri requires adopting timescales that transcend individual human lives. That shift in perspective might prove more valuable than reaching Alpha Centauri itself. Because the real limitation isn't distance, it's thinking. We're trapped in mental models shaped by terrestrial experience, where destinations are reachable within lifetimes, where investments pay off before investors die, where problems have solutions discoverable by the people who encounter them. Interstellar flight breaks all these models. It demands thinking across generations, planning across centuries, accepting that the people who start the journey won't see its completion. This represents fundamentally different relationship with time. Not better or worse, just different. Agricultural societies planted olive trees their great-grandchildren would harvest. Industrial societies built infrastructure their grandchildren would use. Information societies struggle to plan beyond next quarter's earnings report. Interstellar societies, if we become one, must think across timescales that dwarf individual human perception. Alpha Centauri provides focus for that thinking. It's not the only possible target. Other stellar systems might offer better scientific returns or more hospitable environments. But Alpha Centauri holds one irreplaceable advantage. It's closest. That proximity makes it the obvious first step toward broader interstellar capability. Success there validates techniques applicable to more distant systems. Failure there teaches lessons without requiring century-long mission times to other targets. The system's triple nature adds complexity but also opportunity. Proxima orbits roughly 13,000 astronomical units from the Alpha Centauri AB binary pair. That's 400 times Neptune's orbital radius. Vast by solar system standards. Trivial by interstellar standards. A mission reaching Proxima could potentially study all three stars and whatever planets orbit them. One journey, multiple targets. That efficiency matters when each journey costs civilizations total resources. Proxima's flare activity complicates habitability but creates research opportunities. Those flares strip atmospheres from close orbiting planets. They create radiation environments hostile to Earth-based life, but they also provide natural experiments in atmospheric dynamics, magnetosphere interactions, radiation chemistry. Understanding how planets survive or fail to survive such environments informs our understanding of habitability throughout the galaxy. Proxima b likely isn't habitable in any sense humans would recognize. It receives too much radiation. Its atmosphere has probably been stripped. Its surface conditions likely preclude liquid water despite orbiting within the traditional habitable zone. But studying why it's uninhabitable teaches us what habitability actually requires. Each inhospitable world we characterize narrows the search space for genuinely habitable ones. The recent observations suggesting a planet around Alpha Centauri A add another layer. If confirmed, that world orbits a Sun-like star at roughly twice Earth's orbital distance. Too far for traditional habitability, but potentially interesting for other reasons. Gas giants at that distance might host habitable moons. They might have formed closer and migrated outward, clearing debris and creating stable orbits for inner rocky planets we haven't detected yet. They might simply represent another data point in understanding planetary system formation. Each discovery raises more questions than it answers. That's how science works. We don't discover final answers. We discover better questions. Alpha Centauri keeps providing better questions. What determines planetary habitability around M-dwarfs? How do planetary systems form around binary stars? What atmospheric compositions allow liquid water despite high radiation? How does stellar activity affect long-term planetary evolution? These questions drive research that improves our understanding of planets generally, not just those around Alpha Centauri. Every technique developed to study Proxima b applies to thousands of other exoplanets. Every model refined to explain Alpha Centauri's planetary system informs models of planetary formation everywhere. The knowledge compounds. The techniques generalize. The insights propagate. This creates practical value independent of actually reaching Alpha Centauri. Better understanding of planetary atmospheres improves climate models for Earth. Better radiation shielding protects astronauts throughout the solar system. Better propulsion systems reduce costs for satellite launches and deep space probes. The pursuit generates returns long before achieving the ultimate goal, which means failure becomes less catastrophic than you'd expect. Even if we never reach Alpha Centauri, the attempt drives technological development that serves other purposes. Ancient explorers who died searching for the Northwest Passage still advanced geographic knowledge. Early aviation pioneers who crashed still contributed data that made later flight possible. Failed interstellar missions would teach lessons that make subsequent attempts more likely to succeed. This reframes the entire enterprise. We're not betting everything on one impossible goal. We're using that impossible goal to drive systematic progress toward capabilities useful regardless of whether we achieve the specific objective. The journey itself justifies the investment. The destination provides direction, but doesn't determine value. That perspective allows longer timelines without feeling like failure. If reaching Alpha Centauri takes 500 years instead of 200, that's fine. The technologies developed during those centuries serve other purposes. The knowledge gained applies to other challenges. The cultural shift toward long-term thinking benefits civilization generally. The timeline extends, but the value accumulates continuously rather than paying off only at completion. This makes interstellar flight different from other grand challenges. Curing cancer either succeeds or fails. Building fusion power either works or doesn't. Reaching Alpha Centauri generates value throughout the attempt regardless of ultimate success. Every advance toward interstellar capability enables applications within the solar system. Every technique developed for generation ships applies to Mars colonies. Every breakthrough in closed-loop life support serves space stations. The pursuit itself drives progress independent of achieving the final goal. So when people ask, why Alpha Centauri? The answer isn't because we need to get there. It's because aiming there takes us places we couldn't reach otherwise. The destination focuses effort. The journey transforms capability. The attempt changes who we are as a civilization, and that transformation might be what matters most. Not the specific achievement of reaching one particular star system, but the cultural evolution required to seriously attempt it. The shift from quarterly thinking to century thinking, from individual accomplishment to generational progress, from terrestrial perspective to cosmic perspective. These changes ripple through civilization in ways that transcend space exploration. You can't think seriously about interstellar flight without confronting human mortality, without accepting that the people who start the journey won't see its completion, without recognizing that your contribution might be developing one component that enables someone 3 generations later to solve the next problem. That acceptance changes how you think about everything, about legacy, about progress, about what makes life meaningful when your individual existence occupies such tiny fraction of relevant timescales. Alpha Centauri forces those confrontations. It demands we think beyond ourselves, plan beyond our lifetimes, invest in futures we won't witness. And in making those demands, it might teach us something more valuable than how to cross interstellar distances. It might teach us how to think like a civilization that survives long enough to become interstellar in the first place. Perhaps that's the real reason Alpha Centauri matters. Not because we need planets to colonize or resources to extract, but because attempting something this difficult forces beneficial changes regardless of outcome. Consider what happens when a civilization commits to century-scale projects. Investment horizons extend, educational priorities shift, research becomes less focused on quarterly returns, infrastructure gets built for descendants rather than shareholders. The entire cultural metabolism slows down in ways that might actually increase survival probability. Short-term thinking creates fragile systems. Quarterly earnings pressure, election cycles, fiscal years. These temporal frameworks optimize for immediate results at the expense of long-term stability. They encourage exploitation over sustainability. extraction over cultivation, consumption over preservation. But you can't think about Alpha Centauri in quarterly increments. The mission duration exceeds any individual lifetime by orders of magnitude. Success requires institutional continuity across multiple generations. Planning horizons must extend beyond anyone's personal stake in the outcome. That shift in temporal perspective might be more valuable than actually reaching the destination, because civilizations that can't think beyond immediate returns probably don't survive long enough to become interstellar anyway. The filters that prevent most species from spreading beyond their home worlds might be psychological rather than technological. Not, can we build the ships, but can we think far enough ahead to want to? Alpha Centauri provides that test. It demands we prove we can plan beyond ourselves, that we can invest in futures we won't experience, that we can value outcomes our grandchildren's grandchildren might witness. And passing that test changes everything else. Climate change requires century-scale thinking. Asteroid defense requires millennium-scale preparation. Avoiding technological self-destruction requires planning beyond election cycles. All the major challenges facing civilization demand temporal perspectives that Alpha Centauri forces us to develop. So maybe the mission succeeds even if the spacecraft never arrives. Maybe proving we can sustain a multi-generational project demonstrates the cultural maturity necessary for long-term survival. Maybe just attempting something this ambitious shifts how we think about time in ways that benefit everything else we do. There's historical precedent for this. Cathedral construction took generations. Medieval builders laid foundations knowing their great-grandchildren would complete the spires. That multi-generational commitment required cultural institutions that could maintain purpose across lifetimes. And those institutions shaped European civilization in ways that transcended any individual cathedral. The Apollo program lasted barely a decade, but transformed technological culture permanently. Not because we needed moon rocks specifically, but because attempting something that difficult drove systematic innovation across countless domains. The returns came from the pursuit rather than the destination. Alpha Centauri represents that pattern at maximum scale. The pursuit spans centuries. The challenges touch every aspect of technology and organization. The cultural shifts required to seriously attempt it might matter more than whether we ultimately succeed. Which brings us to something subtle about destinations versus directions. When you aim for a specific target, you either hit it or miss. Success is binary, but when you use a distant target to establish direction, you generate value continuously along the vector, even if you never reach the endpoint. Columbus aimed for Asia, but found America. The destination was wrong, but the direction proved valuable. Early aviation pioneers aimed for transatlantic flight, but generated insights that enabled all subsequent aviation. The specific goal mattered less than the systematic pursuit. Alpha Centauri works the same way. Maybe we never reach it. Maybe the mission fails. Maybe we discover something en route that makes the original destination irrelevant. But the direction, outward, beyond the solar system, toward other stars, that direction drives development regardless of whether we reach this particular target. And that might be enough, because the alternative isn't stay home and be comfortable. The alternative is stagnation followed by extinction. Species that stop expanding eventually stop adapting. Civilizations that stop reaching for difficult goals eventually lose the capability to solve difficult problems. Comfort breeds fragility. Challenge builds resilience. Alpha Centauri provides perpetual challenge. Even with perfect technology, the distances involved prevent easy travel. Even with generation ships, the timescales exceed individual lifetimes. Even with everything working optimally, success remains uncertain enough to demand continued innovation. That's actually ideal. Easy goals don't drive sustained development. Once you achieve them, progress stops. But goals difficult enough to require multiple generations of effort create continuous pressure for improvement. The sweet spot isn't achievable in one lifetime, but potentially achievable if we keep trying for centuries, which Alpha Centauri is. Close enough that reaching it seems physically possible. Far enough that doing so requires capabilities we don't currently possess. The perfect distance to drive sustained effort without seeming completely impossible. And there's something poetic about that. Our nearest stellar neighbor sits just beyond reach. Not so distant we can dismiss it as irrelevant. Not so close we can reach it casually. Exactly far enough to require becoming something greater than we currently are. Like the universe placed a test just outside our doorstep. A challenge scaled perfectly to our capabilities, plus several generations of determined effort. Not impossible, but not easy. The ideal difficulty to drive growth without guaranteeing failure. Whether that's coincidence or something deeper remains unknowable, but the functional result is clear. Alpha Centauri occupies the precise distance that makes interstellar travel maximally difficult while remaining theoretically achievable. And that difficulty might be exactly what we need. Because easy goals don't change civilizations. Comfortable challenges don't drive transformation. Only by attempting something genuinely hard do we develop capabilities we didn't know we needed. Only by reaching for targets beyond our grasp do we extend our reach. And maybe that's the ultimate answer to why we should go. Not because we need to be there, not because resources or planets or knowledge await us, but because the attempt makes us better. Because reaching for the stars, even knowing we might never touch them, elevates us beyond what we'd become if we stayed comfortable. The cosmos offers no guarantees. Alpha Centauri might prove barren. The journey might fail. Everything we invest might generate nothing but expensive lessons. But those lessons themselves might be what saves us. The capabilities developed might be what prevents extinction. The cultural transformation might be what allows civilization to survive its own power. In which case, the mission succeeds regardless of whether the spacecraft arrives. Because the point was never really about reaching one particular star system. It was about becoming the kind of civilization capable of trying. About developing the long-term thinking, the institutional stability, the technological capability, and the sheer audacity required to attempt something this difficult. Those qualities matter far beyond space exploration. They're probably necessary for any civilization that survives contact with advanced technology. The filters that destroy most species might select specifically against short-term thinking, institutional fragility, and lack of ambition. Civilizations that can't attempt multi-generational projects probably can't survive the challenges that technology inevitably creates. Alpha Centauri tests whether we pass that filter. Not by providing resources or destinations, but by demanding we develop the civilizational maturity necessary to attempt it. And in demanding that maturity, it might give us the one thing we truly need. Not more planets or more knowledge, but more time. The temporal perspective necessary to survive our own cleverness. Because that's the real challenge. Not building the ships or solving the physics or surviving the journey. It's thinking far enough ahead to want to. It's valuing futures beyond our own lifetimes. It's investing in outcomes we'll never witness. And civilizations that learn to do that might be the only ones that survive long enough to actually reach the stars. Which means Alpha Centauri offers something more valuable than any destination. It offers the question that determines whether we become something greater or remain trapped by our own short-sightedness. And how we answer that question, whether we seriously attempt the journey or dismiss it as impractical, might determine everything that comes after. The stars aren't going anywhere. They'll still be there in 1,000 years, 10,000, 1,000,000. But whether we'll still be here to reach for them depends entirely on choices we make now. On whether we can think beyond ourselves, beyond our lifetimes, beyond everything that makes thinking difficult but meaningful. Alpha Centauri sits there in the southern sky, neither approaching nor receding at any pace that matters to human timescales. A triple star system, 4.37 light-years distant, close enough to tantalize, but far enough to demand we become something greater than we are. The perfect test, the ideal challenge, the question that might matter more than any answer we could possibly give it. The question was never really whether we can reach Alpha Centauri. The question was whether we're the kind of species that tries. Every technological civilization faces this test eventually. The moment when comfortable expansion within a home system becomes insufficient. When the easy resources are claimed, the obvious destinations visited, the simple problems solved. What comes next determines everything. Some species probably stop. They build comfortable homes on comfortable worlds and optimize for comfort until something, resource depletion, stellar evolution, cosmic accident, ends them. They never develop the capabilities that might have saved them because those capabilities only emerge from attempting difficult things. Other species keep reaching, not because reaching guarantees success, but because the attempt itself transforms what's possible. They aim for targets beyond their grasp and discover their reach extends further than they thought. They invest in futures they won't witness and create legacies that outlast their individual existence. We don't know yet which kind we are. The verdict isn't in. But Alpha Centauri offers the test that determines the answer. Every advance toward interstellar capability, whether we ultimately use it or not, makes us more resilient. Better propulsion means faster response to asteroid threats. Better life support means viable off-world colonies. Better long-term planning means surviving challenges that require century-scale solutions. The capabilities themselves matter more than the destination that inspired them. And maybe that's the real gift of those distant worlds orbiting Proxima Centauri. Not that they exist specifically, but that knowing they exist changes us, makes the galaxy feel less empty, makes other stars feel less like abstract points of light, and more like neighborhoods we haven't visited yet, makes interstellar space feel less like an insurmountable barrier, and more like an ocean we haven't learned to cross. Humans crossed oceans before we understood ocean currents. We flew before we fully understood aerodynamics. We ventured into space before we'd solved the engineering challenges that made space travel routine. The pattern holds. The destination comes first in imagination, then in aspiration. then in capability developed specifically to reach it. Alpha Centauri follows that pattern. Today it's imagination, the worlds we think might exist there based on fragmentary observations. Tomorrow it becomes aspiration, the place we decide we want to reach even knowing the difficulty. Eventually it becomes capability, the technologies we develop specifically to make the journey possible. That progression takes time, probably more time than any of us have individually. But time scales differently for civilizations than for people. What seems impossibly long from a human perspective becomes merely challenging from a civilizational one. And civilizations that survive learn to think on civilizational timescales. The students studying aerospace engineering today won't build the ships that reach Alpha Centauri, but they'll build the ships that prove interstellar flight is possible. Their students will push the capability further, and their students further still, until someone looks up and realizes the impossible became difficult, the difficult became expensive, and the expensive became merely challenging. That's how species transcend their home systems. Not through sudden breakthroughs, but through accumulated progress across generations. Each generation pushing slightly further than the last. Each advance making the next advance slightly easier. Each impossibility becoming slightly less impossible until it transforms into something merely hard. We're at the very beginning of that progression. The first generation to know planets orbit our nearest stellar neighbor. The first to seriously consider what reaching them might require. The first to face the choice between attempting something impossibly difficult and accepting permanent confinement to one solar system. How we respond to that choice matters more than whether we succeed. Because the attempt itself, the serious, sustained, multi-generational attempt, transforms us in ways that determine whether we survive long enough to become truly interstellar. And that transformation might be what the universe is waiting to see. Not whether we can build the ships, but whether we can think far enough ahead to want to. Not whether we solve the physics, but whether we develop the cultural maturity to sustain century-scale projects. Not whether we reach other stars, but whether we become the kind of species that reaches for them. Alpha Centauri sits there waiting, not judging, not caring, just existing as it has for billions of years. A triple star system with planets orbiting in the habitable zones, 4.37 light-years distant, close enough to obsess over, but far enough to require becoming something greater than we currently are. The perfect test. The ideal challenge. The destination that matters less than the journey it inspires. And how far we get toward reaching it might determine everything about what we become, and whether we survive to become anything at all. The stars aren't going anywhere. They'll wait as long as it takes for us to figure out whether we're reaching for them or not.